Good morning. Before starting the presentation, I would like to thank the organizers for having invited me for the speech of today about problems and perspectives in seismic risk analysis of major hazard industrial facilities. I would like also to thank my research team for the strong support received in developing most of the topics I will speak about. This is the problem statement. The past earthquakes demonstrated the high vulnerability of hazardous non-nuclear industrial facilities, especially chemical and petrochemical plants, against natural hazards, leading to huge economic losses, injuries, and fatalities, beyond the unrecoverable damage to the environment. So we are speaking about up to 5% of industrial accidents triggered by natural hazards, the so-called NATEC events, among which the earthquake represents a fearsome cause, as clearly demonstrated in the past. And this is because petrochemical plants are often located in high seismic and populated zones. So this leads to the conclusion that seismic vulnerability should be included in major hazard process plant risk assessment. These are only some examples of NATEC events occurred during catastrophic earthquakes from Northridge 1994 to Tohoku earthquake in 2011. So according to the questionnaire survey by the Fire and Disaster Management Agency, the facilities damaged by the 2011 Tohoku earthquake in Japan amount to more than 3,000. This is about 2% of the total surveyed hazardous materials facilities in the East Japan area. So they had 1,400 hazmat facility damaged by the strong motion, and about 2,000 hazmat facilities were damaged by the tsunami effects. And the fire occurred in the 42 facilities with oil leakage that occurred in more than 120 facilities, like in the pictures. This is the most famous accident occurred in the Chiba refinery during the earthquake. Beyond the clear needs to tackle the problem of setting up methodologies for NATEC risk assessment, some additional problems are to be faced. So there is a general lack of specific rules and standards suggesting clear methodologies. Moreover, there are general inconsistencies of procedures for seismic hazard assessment in presence of hazmat industrial installations. And finally, the high multidisciplinary character of the quantitative risk assessment that includes structural engineers, geologists, and chemical industrial engineers renders the matter complicated. This multidisciplinary character generates an additional aspect that, together with my colleagues, we called communication problem. So basically, the different background of the experts and different scale of the problem induce the additional difficulty of communication among technicians from micro to meso to macro scales. To simplify this aspect, there are at least two levels: component level, where methods of structural engineers are required, and system level, where methods from experts of process safety analysis are required. The general lack of specific rules and standards on this matter can be noticed. For example, in Europe, we have a dedicated directive, the so-called Seveso III, that explicitly considered NATEC events, but without providing specific methodologies for the risk assessment. In the USA, the guidelines of American Society of Civil Engineers provides design rules for equipment rather than risk assessment criteria. In general, most of the international standards often used by oil and gas industry do not cover adequately the risk assessment and do not suggest a recognized approach. For example, Eurocode 8 Part 4, that is entirely dedicated to some critical equipment, like tanks and pipelines, do not cover adequately the risk assessment procedure. All these difficulties generate a prudent attitude among designers and owners of hazardous plants. For example, to comply with the Seveso 3 directive, design PGA is fictitiously increased by applying an important factor, leading to extremely safe and conservative design. Moreover, because of different important factors used in European countries, this leads to a non-uniform hazard design. To complete the overview, I need to highlight the inadequacy of the existing quantitative risk assessment methodologies based on technological hazards only. Moreover, codes and standards for civil and nuclear structures cannot be directly applied to non-nuclear plants, and thus an effective methodology to perform quantitative seismic risk assessment of hazardous facilities is needed, which should include all the above relevant aspects. To better understand the main issues in the risk analysis of hazardous industrial plants, like petrochemical plants, let's consider a nuclear power plant. That is different. To better understand this difference, let's see these. As well known in this case, in case of nuclear power plant, the risk is mainly governed by main events, the core melt, and it is enough to use a fault tree to identify the main critical components that contribute to the generation of the accident and mitigate the risk in this way. But in case of NATEC events, the situation is really different. We have a multiplicity of accidents generated by earthquakes. For example, the red dots here that are equipment that are damaged during the earthquake. But these can in turn generate multiple chains of accidents, like the red arrows that can hit in terms of physical effects the yellow equipment, the secondary damage units, and so on, in a domino effect fashion or escalation effects. So in this respect, phasing up the problem using a multiple level approach appears rather suitable, but really difficult. So in this slide, the key aspects of quantitative seismic risk assessment are synthesized in this very well-known integral that includes the component level and the system level as defined before. Thus, a probabilistic approach in the framework of performer-based earthquake engineering, which now it includes also a consequence analysis, is suggested. Let's start analyzing the several aspects that characterize quantitative seismic risk analysis, highlighting the most critical ones. So let's start with the seismic hazard characterization. So the adoption of a performer-based seismic analysis approach entails the definition of limit states. In the civil field, serviceability and ultimate limit states are typically adopted. But how to translate these in the industrial field? So the nuclear field can help us where two limit states have been adopted: design basis earthquake and safe shutdown earthquake. The first one represents the earthquake for which the plant is still operative and without damage. Safe shutdown earthquake is related instead to a certain level of damage but without consequences in the safe shutdown conditions. The question is how to calculate the probability of occurrence of an earthquake capable to generate these limit states. In the literature, a return period of 475 years is generally accepted for DBE and soil class A. More involved is the case of SSE, that sometimes could entail very high return periods that are not currently included in the codes. Thus clearly emerges the need to set up a QSRA methodology using which the return period can be finally evaluated. Other relevant aspects characterizing the seismic hazard are the following. First of all, the question is what ground motion prediction equation should be used. For example, only local as suggested by nuclear power plant field, or ones derived from a wide regional area. This is really an open issue. The local effects of the soil could also have a crucial role in the risk assessment of industrial facilities, because they are often very large, entailing different soil classes in the same plant. In addition, high vibration periods, which are often present in industrial equipment, as for example for the convective motion in the broad storage tanks, that can have very large vibration periods, up to 10-12 seconds. So the definition response spectrum in this range of period could represent a serious problem, as you know. And finally, the record-to-record variability in case of multi-frequency behavior could really represent a problem. The difficulty is to recognize sufficient practical scalar vector value intensity measure to scale the records. But the limited experience in this field is currently present in the literature. Seismic vulnerability of structures and equipment is traditionally expressed in the form of demand fragility curves, with the form indicated in the equation. So the main issues related to this definition here indicated are very well known. However, concerning industrial equipment, the definition of proper model in case of strong nonlinearities and fluid structure interaction effects, as for example in the storage tanks, could have a certain importance. High fidelity models could entail a high computational effort. On the other hand, simplified models could entail big errors. And in addition, random effects in the characteristic of structures could have a crucial role, as demonstrated in the literature. Thus, a study of possible surrogate models is strongly suggested. But also the selection of proper intensity measure, well correlated with response, is an open issue, along with the recognizance of proper engineering demand parameters and damage, and the engineering demand parameter consistent damage states and limit states. Another list of criticalities is here provided, which included several questions. First of all, are libraries of fragility curves available in the literature usable for risk analysis of industrial plants? So these libraries are often limited in numbers and type of equipment, and thus they are often incomplete, obliging to build specific fragility curves. Moreover, how much is the error related to these standard fragility curves? So the experience evidenced that it could be very high. Finally, the degradation phenomena are often absent in the definition of fragility curves, even though for industrial equipment the aggressive environment could render this aspect crucial. So the recognition of equipment classes based on equipment typology and possible damage could help the selection of proper engineering demand parameter and damage states. Here an example extrapolated from the paper indicated in the slides, where the analysis of databases present in the literature has been used for the purpose. However, more needs to be done, especially where the behavior is complicated by the interaction between secondary elements and primary structures. In the slide, some pictures of very recent shaking table tests are shown that has been performed within the SPIF project, a translational access of a European SERA project, where a multi-story frame equipped with storage tanks and pipes has been tested demonstrated that local effects and dynamic interaction between secondary and primary elements could be crucial, and the evaluation of leakage for critical fittings like bolted flange joints could be of paramount importance. Seismic damage can induce loss of content, generating in turn a physical effect, explosion, fire, and so on the surrounding equipment, activating with the right conditions other accidents, generating the so-called domino effects. In this respect, three are the main issues. What kind of a relation between damage states and loss of containment could be identified? For example, we could focus on a deterministic or probabilistic approach. What are the critical equipment for which the loss of containment could induce escalation phenomena? And finally, the target equipment able to propagate the damage should be also identified. Of course, concerning the first aspect, an experimental approach is typically suggested to calibrate analytical models. However, a few number of experimentations are currently available in the literature. To answer the first question, a possible approach is to demonstrate loss of containment matrices, like the one in the figure, that relate the two aspects in a deterministic manner. Standard loss of containment events can be used, trying to identify for each lock event the damage able to generate it. This approach has been suggested in the paper indicated above. So for each element, the effect of damage propagation can be determined by using specific event trees, or for each source and target units, along with models for determination of physical effects, thermal radiation over pressure, that are more related to the chemical worlds, industrial worlds, to derive the related consequences. In all the slides, I suggested some readings that can help you to follow and to understand better details on this page. In the domino chains propagation modeling, two different approaches can be used. Probit functions that are used to derive the probability of damage for a given intensity of the physical effect. And the second is conventional damage zone, where conventional threshold value of the physical effect intensity is reached. In the pictures, there is a simplified scheme of the first one. This is an exhaustive list of quantitative seismic risk assessment methods proposed in the literatures. Some approaches are fully empirical, whereas some others are based on analytical numerical approaches like Monte Carlo simulations. Some softwares are also available. However, a QSRA methodology, including in a detailed and realistic manner all steps listed before, is not yet available, despite more than a decade of research effort. A recent proposal comes from my research group that tried to solve most of the issues listed before. A practical software developed in a MATLAB environment has been proposed, which is based on Monte Carlo simulations. A multi-level approach is used where the level greater than 1 are dedicated to the domino effects, which is based on probit functions and classical methodologies to derive physical effects. The risk can be expressed both in terms of economic losses and individual and societal risk. These two last metrics are typically adopted in classical QRA. Some of the strengths and limitations of quantitative seismic risk assessment methodology, as used in some technological sectors, as chemical process plants, has been discussed. And the main conclusions are the following. Process plants require different QSRA methods with respect to nuclear plants or civil structures, as well as traditional QRA methods for chemical plants. So the two worlds must talk. Multiple starting scenarios and simultaneous interacting chains of accidents should be modeled in a dynamic manner. A novel automatic method to systematically generate starting scenarios and keep track of accident chains is needed. In this respect, Monte Carlo simulations appears credible. Reliable information about equipment fragility and possible damage states are required, and credible correlation between structural damage and loss of containment is needed. Some further technical issues to be solved are here listed, in particular how to automate the damage propagation process modeling, and this is really an open issue. Monte Carlo simulation appears also in this case credible. Vulnerability curves are needed in case of superposition effects from exposure to multiple source event of different type. Cumulative damage from superposition, seismic input and other physical effects needs to be assessed. For example, what happens when the structure has been weakened by exposure to other damaging factors. And finally, how to manage piping, equipment, and multi-level structures to the right fragility models. These are some of the open issues for future research. Around the world, there are many working groups that are dealing with several aspects that we've spoken today. One of these is Working Group 13 of the European Association of Earthquake Engineering that is working on seismic assessment, design, and resilience of industrial facilities. This is the long list of partners, many universities and institutions with different expertise in the field of seismology, earthquake engineering, resilience, and attack risk. It is coordinated by me and by Professor Christoph Gutenberg of Aachen University. And the idea is to cover all the aspects that we discussed today. Another very active working group is the Seismic Engineering Technical Committee of ASME, Pressure Vessel and Pipe Division, whose chair is Professor Zanfruia, has been the chair during the last 4 years. Every year we organize within the ASME PVP conference a series of special sessions dedicated to the topic of my speech, trying to stimulate the comparison to solve problems. So who is interested in joining us, please keep in touch with Professor Fruia. So with this last slide, I end my presentation, and thank you very much for your attention.